Thank you for listening. This course was created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional podcasts, books, newsletters, and cool merchandise await. Let's get started. Federated and edge approaches represent a shift in how artificial intelligence systems are designed and deployed. Instead of centralizing all data and computation in massive cloud environments, these methods bring processing closer to where the data resides. This architectural change reduces the need for moving sensitive information across networks, thereby lowering exposure and improving privacy. At the same time, efficiency is gained by cutting down on bandwidth demands and enabling faster responses. For organizations, this distributed model supports compliance with increasingly strict data localization laws, while also offering resilience in the face of outages or disruptions. In short, federated and edge methods are about decentralizing intelligence without losing the benefits of collaboration. Federated learning is one of the most well-known techniques in this space. The idea is straightforward. Instead of sending raw data to a central server, each device or participant trains a local version of the model. Updates from these local models are then aggregated to form a global model that improves collectively. Crucially, no raw data ever leaves the participant's device, which preserves privacy while still allowing collaboration across large populations. This method has gained traction in areas like mobile phone personalization, where millions of devices contribute to a shared model without sacrificing the confidentiality of user inputs. Federated learning demonstrates that privacy and collaboration are not mutually exclusive. Edge computing, while related, focuses more broadly on deploying AI directly on local devices or servers. Rather than relying on a centralized data center, decisions can be made close to the source of data generation. This brings several advantages: lower latency, reduced bandwidth use, and less dependency on central infrastructure. For example, an industrial sensor can process data on-site to detect anomalies in real time, without waiting for information to travel to the cloud and back. Edge computing also enhances resilience, allowing systems to keep functioning even when connectivity is interrupted. By moving intelligence to the periphery, edge computing supports both performance and autonomy. The benefits of federated approaches extend across multiple dimensions. They protect sensitive user data by minimizing exposure, since information never leaves local environments. They also enable large-scale collaboration, making it possible for hospitals, banks, or universities to pool insights without pooling raw data. Compliance with localization laws is another advantage, as federated systems can respect jurisdictional boundaries more easily. Finally, federated learning reduces the risk of centralized breaches. There is no single repository of raw data to target. These benefits explain why federated learning is increasingly being considered for sensitive applications where both collaboration and privacy are essential. Edge approaches bring their own unique set of benefits. Chief among them is speed. By processing data locally, systems can deliver rapid responses in contexts like autonomous driving or medical monitoring, where milliseconds matter. Reduced reliance on cloud infrastructure also lowers costs and dependency risks, while giving users stronger data sovereignty since their information does not need to leave their devices. Scalability is another advantage, as edge methods can be deployed across thousands of devices simultaneously, creating distributed intelligence networks. The combination of faster decision-making, greater independence, and improved privacy makes edge computing a compelling complement to traditional centralized models. Of course, federated learning is not without challenges. One issue is the heterogeneity of participating devices. Not all contributors have the same computing power, bandwidth, or data quality. This unevenness can make aggregation more complex. Communication overhead is another problem, since frequent updates must be coordinated across potentially thousands of participants. Malicious contributions, such as poisoned updates, also pose risks that must be mitigated through secure aggregation and monitoring. Finally, managing privacy budgets across distributed nodes adds another layer of complexity. These challenges highlight that while federated learning is promising, it requires careful governance and robust technical safeguards. Edge computing, too, presents its own challenges. Local devices often have limited hardware resources, which can constrain the complexity of models they can run effectively. This makes lightweight model design a necessity, but it can also limit performance in certain use cases. The decentralized nature of edge systems also increases the need for frequent updates and patching, as each endpoint must be kept secure and current. Distributed endpoints expand the attack surface, making them vulnerable to tampering, malware, or physical compromise. Synchronizing global models across numerous edge devices is another difficulty, as delays or failures in updates can create inconsistencies. These hurdles underscore the trade-offs inherent in moving intelligence out of centralized environments and into distributed infrastructures. The synergy between federated learning and differential privacy provides a powerful pathway to stronger safeguards. When distributed training is combined with noise addition, the protection of individual data points is significantly enhanced. Even if adversaries attempt to analyze model updates, the noise ensures that they cannot reliably infer details about specific participants. This hybrid approach balances accuracy with confidentiality and has been widely researched in sensitive domains like healthcare and finance. It demonstrates how federated and privacy-preserving techniques can reinforce each other, offering organizations both collaboration and robust protection without forcing a binary choice between the two. Security considerations are paramount in both federated and edge systems. Encryption of local updates helps ensure that data transmitted during aggregation cannot be intercepted or tampered with. Device authentication is critical, as malicious actors might otherwise attempt to impersonate legitimate participants. Monitoring is needed to detect poisoned contributions, where adversaries intentionally feed harmful updates into a shared model. Protecting against model leakage, where outputs reveal more than intended, adds yet another layer of responsibility. Without these safeguards, federated and edge systems could ironically introduce new vulnerabilities, even as they solve existing privacy problems. Security, therefore, must be designed hand in hand with decentralization. Applications of these approaches are already visible in sensitive domains. In healthcare, federated learning enables hospitals to collaborate on research without sharing raw patient data, unlocking insights that no single institution could achieve alone. In finance, distributed transaction models support fraud detection and risk analysis across institutions while protecting individual accounts. On consumer devices, predictive typing models are trained locally on smartphones, preserving user privacy while improving performance. In industrial IoT, edge systems monitor machinery in real time, reducing downtime and improving safety. These examples illustrate the breadth of applications where federated and edge methods can provide both efficiency and ethical safeguards. Operational considerations play a large role in determining whether federated and edge methods succeed in practice. Orchestration platforms are required to manage the complexity of coordinating thousands of devices, ensuring updates are properly aggregated and applied. Monitoring model convergence is critical, as inconsistent updates can stall progress or reduce performance. Handling asynchronous contributions, where devices update at different times, requires robust scheduling mechanisms. Ensuring auditability of these processes adds another layer, since regulators and stakeholders will expect visibility into how systems are governed. These operational layers are as important as the technical design, ensuring that distributed AI functions reliably at scale. Regulatory alignment is one of the strongest arguments for federated and edge adoption. By keeping data local, these methods inherently support compliance with data localization mandates that restrict cross-border transfers. They also make it easier to demonstrate compliance with privacy laws, since sensitive information is not centralized in ways that regulators often view as risky. Organizational governance goals such as accountability and minimization are also supported by decentralization. As AI-specific regulations evolve, federated and edge approaches are likely to be explicitly recognized and even encouraged as methods of responsible deployment. In this way, they align technical innovation with legal and ethical expectations. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Scalability is one of the most pressing questions for federated networks. When only a handful of participants are involved, coordination is relatively straightforward. But as networks expand to thousands or even millions of devices, communication efficiency becomes critical. Researchers are developing optimized aggregation methods that reduce the volume of data exchanged while maintaining accuracy. Balancing convergence speed with privacy protection is another challenge, as more participants mean more variation in the data and devices contributing. Robust aggregation techniques, such as secure multi-party computation or Byzantine resilient protocols, help prevent malicious contributions from derailing training. These innovations are steadily making federated learning viable at scales once thought impractical. Edge systems face their own scalability considerations. Wide deployment across devices requires consistent, secure distribution of updates, which becomes complex as the number of endpoints grows. Central orchestration platforms can coordinate updates, but they must do so without undermining the very autonomy that makes Edge appealing. Resource allocation also becomes a balancing act, as not all devices will have equal processing power or connectivity. Ensuring fairness across heterogeneous devices requires adaptive strategies that can tailor workloads. Ultimately, scaling edge systems is about finding harmony between local independence and global coordination, ensuring that performance and security are maintained even as networks expand. Monitoring and governance are vital in decentralized systems where control is distributed. Continuous assessment of local contributions ensures that the integrity of the global model is preserved. Central oversight, while lighter than in traditional architectures, is still necessary to provide compliance evidence and enforce standards. Logging mechanisms must be in place to capture activity across participants, providing accountability in case of disputes or incidents. Integration with enterprise governance systems helps unify these processes, ensuring that federated and edge methods are not isolated but part of broader accountability frameworks. Governance thus becomes the glue that holds distributed systems together. Trade-offs are inherent in federated and edge approaches, and they must be carefully managed. Latency improvements may come at the cost of reduced model accuracy if local devices cannot handle complex updates. Privacy can conflict with computational efficiency, as adding protections like differential privacy introduces overhead. Organizations must also weigh local autonomy against centralized control. Too much independence may fragment the system, while too much centralization erodes the benefits of distribution. Infrastructure costs must be balanced against the efficiency, compliance, and trust gains these methods deliver. Navigating these trade-offs requires a clear understanding of organizational priorities and risk tolerances. Technological enablers are making federated and edge approaches increasingly feasible. Advances in lightweight AI models ensure that even resource-limited devices can contribute meaningfully. Secure aggregation protocols safeguard updates during training, while orchestration platforms simplify coordination across large networks. The rollout of 5G connectivity further enhances the promise of edge computing by enabling fast, reliable communication between devices. These developments reduce many of the barriers that once limited adoption, opening the door for federated and edge systems to be deployed at industrial and societal scales. Technology is not just catching up to these ideas, it is actively propelling them forward. Future directions suggest a broadening of scope for federated and edge methods. Expansion into multimodal learning tasks will allow distributed systems to handle text, images, audio, and sensor data simultaneously. Integration with generative AI systems could bring privacy-preserving collaboration into fields like content creation and natural language interaction. Global collaborative research may increasingly adopt federated models, allowing institutions in different jurisdictions to share insights without sharing raw data. Standardization of architectures will likely follow, ensuring interoperability across platforms and reducing the fragmentation that currently challenges large-scale adoption. The future of federated and edge is one of increasing maturity, scalability, and mainstream acceptance. Organizational responsibilities play a central role in making federated and edge approaches sustainable. Providing the necessary infrastructure is only the beginning. Teams also need training in distributed system design, orchestration, and security. Staff must understand not only the benefits but also the limitations, ensuring they are prepared to troubleshoot issues such as uneven device performance or malicious updates. Compliance monitoring cannot be left to chance. Organizations must embed oversight mechanisms that check adherence to privacy and security requirements. By weaving privacy principles directly into design processes, teams ensure that decentralization does not compromise accountability. In practice, this means that federated and edge initiatives succeed only when organizations treat them as enterprise priorities rather than experimental add-ons. From a practical standpoint, several takeaways stand out for practitioners. Federated and edge methods provide significant privacy and efficiency benefits, but they come with real challenges. Device heterogeneity, security risks, and infrastructure demands require deliberate strategies and governance to manage effectively. Strong monitoring systems and structured oversight processes are essential to prevent vulnerabilities from spreading across distributed networks. Synergy with differential privacy and secure aggregation protocols can reinforce protections, offering both collaboration and confidentiality. Practitioners should view these methods as promising but not effortless, requiring both technical expertise and organizational commitment to deliver their full potential. Looking ahead, the forward outlook is highly favorable. Commercial adoption of federated and edge methods is expected to accelerate, driven by the dual pressures of regulatory compliance and user demand for stronger privacy. Emerging AI regulations are likely to reinforce these methods as acceptable and even preferred solutions, especially in sensitive industries like healthcare and finance. Broader use across research and industry will make orchestration platforms more robust and user-friendly, reducing barriers to entry. As tools improve, organizations will find it easier to deploy federated and edge approaches at scale, embedding them into everyday AI practice rather than treating them as experimental projects. The key points of federated and edge methods can be summarized clearly. They decentralize processing, bringing computation closer to where data is generated. Benefits include stronger privacy protections, faster responses, reduced reliance on centralized infrastructure, and easier compliance with localization laws. Challenges remain, especially device heterogeneity, synchronization, and governance, but research and practice continue to address these obstacles. Future growth will be tied to advances in lightweight models, orchestration platforms, and communication infrastructure. These points underscore that federated and edge are not niche approaches but foundational strategies for the future of AI. In conclusion, federated and edge methods represent a powerful rethinking of how artificial intelligence can be built and deployed. By decentralizing computation, they align privacy, efficiency, and compliance in ways that centralized systems often cannot. Effective governance, monitoring, and technical safeguards are necessary to manage trade-offs and mitigate risks, but the benefits are substantial. As adoption grows, synergy with methods like differential privacy will further strengthen protections. The trajectory points toward a future where distributed intelligence becomes mainstream, supported by regulation, infrastructure, and organizational maturity. This naturally sets the stage for the next episode. Synthetic data. While federated and edge methods focus on protecting real data through distribution, synthetic data offers another powerful pathway by creating artificial datasets that preserve utility without exposing individuals. Exploring how synthetic data complements these approaches expands the toolkit for building AI systems that are both innovative and responsible. Thanks for tuning in to Bare Metal Cyber, your trusted source for cybersecurity educational materials, news, and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.